Okay, so let's get started. This is week 6 of interactive live sessions for the course on fluid dynamics and turbomachines. This course is being offered by NPTEL and is being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee, both from the Department of Mechanical Engineering at IIT Madras. My name is Debjit. I'm the TA for this course, and like every other week, we shall be solving some practice problems together and having discussions regarding anything and everything related to the course. So, without any further ado, let us get started. But first, let me check whether I'm uh, properly audible and visible and whether my slides are visible or not. Can you please confirm? And yes, you can ask questions anytime you want.
Good afternoon, sir.
Hello.
Am I audible?
Yeah.
Sir, myself Akash, sir, and today only I just joined this course. This
Session.
meeting.
Yeah.
Uh, Sir, actually, I have few queries regarding exam.
Okay.
Sir, first is that while writing exam, is there any kind of negative marking will be there in paper?
Probably not. See, I'm not the right person who knows the exact details of the exam pattern and all that, but as far as I know, I can't confirm 100%, but I don't think negative marking is there.
Sir, if there is any kind of say numerical question came,
Hmm.
will I able to use calculator my own or
No,
they will
no.
provide?
There will be a online digital calculator in the computer-based exam, so you'll have to use that particular calculator.
Sir, is it like how we used to give in gate exam?
Sort of, yeah, similar.
That but that kind of calculator only will be there,
Yeah,
no?
yeah.
Okay, sir.
Anything else? Okay, so whenever you feel like you want to ask something or make any comment, please don't hesitate to do that. We shall get started now. So, let's see. Yeah. So here's question number 1 of today's session, which is asking us that uh, the hydraulic efficiency of a pump is defined as what? So there are 4 options given below. Uh, Option number A says that it's the ratio of power delivered to the shaft to the fluid input power. Option B says it's the ratio of useful fluid energy delivered to the total fluid energy supplied. And option C says it's the ratio of total power output to the total power input. Option B says that it's the ratio of volumetric energy delivered to the shaft energy input. So what is the correct definition of the hydraulic efficiency, sorry, of the hydraulic efficiency of a pump? Is it option A, the ratio of power delivered to the shaft to the fluid input power? Is it option B, the ratio of useful fluid energy delivered to the total fluid energy supplied? Is it option C, the ratio of total power output to the total power input? Or is it option D, the ratio of volumetric energy delivered to the shaft energy input? So read the questions carefully, and once you have figured out the solution, you can either type in the chat box or you can unmute and answer as well, whichever way you feel comfortable. So in week 6, our discussions has been on the different forms of efficiencies as well as the related different forms of losses. What happens in the non-ideal flow situations, and also we learned about how to use velocity triangles at the uh, pressure side as well as the suction side of any given turbo machine, and uh, use that to compute the energy interactions between the fluid and the turbo machine. So coming back to question number 1, it's asking us that the hydraulic efficiency of a pump is defined as what? Is it option A, the ratio of power delivered to the shaft to the fluid input power? Is it option B, the ratio of useful fluid energy delivered to the total fluid energy supplied? Is it option C, the ratio of total power output to the total power input? Is it option D, ratio of the volumetric energy delivered to the shaft energy input in any given pump? Any guesses? Okay, so let's take a look at the solution. It's actually option B, the ratio of useful fluid energy delivered. This word is important. Useful fluid energy delivered to the total fluid energy supplied. What does this mean? So basically, before the fluid comes into contact with the impeller and the rotors, so there is some fluid channels associated within the pump. This is not part of the piping before the pump. So within the pump, there are flow channels in which sudden expansions and bends and turns can happen, which can result in a hydraulic loss of the total head supplied before. So let's say if I have a reservoir somewhere here, there, uh, there's a total head of say h meters being supplied. That's not the entire uh, fluid energy is not really uh, what acts as the actual input to the pump impeller. So uh, which is why there could be losses, and the ratio between that useful energy which the pump gets to exploit versus the total fluid energy coming into it, that's what the hydraulic efficiency is. Okay. Uh, my is my video visible or did it stop working? I think there's some issue. Can you see my video? Yeah. All right. So let's. I hope things are okay. Let's carry on. So we will move on to question number 2 now, which is asking us that the slip factor in a centrifugal pump analysis accounts for what? Is it option A, losses due to bearing friction? Is it option B, difference between actual and ideal tangential velocity of fluid at blade exit? Is it option C, variation in the inlet velocity profile? Or is it option D, the variation in static pressure at the pump outlet? Okay, so B, okay, the difference between the actual and ideal tangential velocity of fluid at the blade exit. So let's take a look at the solution. It's actually option B. Good. So, what happens is, let's say if I have a blade designed like this, and I'm intending that the flow comes out with a relative velocity tangential to the blade, but what happens is that due to uh, pressure differences as well as non design off design operation of the pump, there could be a difference in this ideal uh, relative velocity, or rather the ideal tangential velocity. So the actual tangential velocity and the ideal ones are different, and as a result, the this brings in additional losses, and the uh, efficiency or power delivery that we can compute using the Euler's equations, the an error creeps into that computation. So there is a mismatch between the two, and that is what the slip phenomena does, and the slip factor sort of captures that. Good. Any questions on this? Okay, so if not, we will keep moving. We will move on to question number 3 now, which is asking us that in a centrifugal pump, leakage losses are primarily caused by what? Is it option A, fluid escaping through clearance between the impeller and the casing? Is it option B, energy loss due to reverse flow circulation? Is it option C, vortex breakdown near the inlet? Or is it option D, reduction in the shaft speed? So leakage losses, what is that caused by? Regarding strategy, whatever you have in mind, you can ask. Go ahead. You can unmute and ask.
So, like I told you that, sir, can you please suggest that from now onwards, if I want to go for this preparation part,
Hmm.
like I have done my around till fluid mechanics, I have done,
Hmm.
and few means I'm going for this now thermodynamics part. So,
Okay.
how to proceed now to have like good marks in exam?
Okay. So see, you have to cover the basics first. That for that, I think going through the lectures and the assignments that you have should be sufficient enough. And there are, see, all the theory parts. I'm sure you can do well on them just by reading up and covering all the materials. The challenge lies in solving the numericals properly. And if you really look closely, there are only a few types of, or few topics in uh, the numerical analysis part that's important. And if you cover that well, then any sort of question you'd be able to answer. So a few of them that I can think of right now top of my head is, let's say, from this week, it's these velocity triangles and how to use them to solve problems. Then another part would be the finding out the total to total, the static to static, static to total efficiencies in turbo machinery. So for that, you need a little bit of thermodynamics, so that basically either the temperatures would be given or the pressures would be given, and you have to find the other variable. And for that, you need to apply the isentropic expansion or contraction formula, and then relate that to enthalpy, and those differences would give you the answer. So these sort of things, like there are few particular uh, topics from which numericals can come, and if you just understand the basic principles of them, then you're good to go.
So actually, one more problem is like uh, I missed two assignments,
Okay.
and two assignments I missed. But after means I'm just uh, keeping the assignments are like ongoing, sir. Means I
Hmm.
haven't missed other assignments. So will it be sufficient for me to have a certificate?
Yeah, I think so. I'm
Like
not
if
really
I
sure of
keep on.
the marking scheme and all that, but if you have specific questions, you can just write to the NPTEL team regarding the exact rules of it, like if you miss assignments, then whether you're eligible or not, those sort of questions.
Say NPTEL team.
Yeah.
Okay, sir.
Also regarding the marking scheme of the exams,
Mm-hmm.
I can help you as much as possible with the the course content side of things. I'm not really aware of all these rules, so as you can understand by now,
Okay, okay,
so
sir.
I'm not the right person to help you.
So, sir, can you please tell me that these questions which you are sharing now,
Hmm.
where can I get these questions?
So a link is there in the what is that, the course web page.
Okay, sir.
So after every session, I upload these slides along with the the questions as well as the solutions. So there's a Google Drive in which you can find all these slides.
Okay, sir.
What about this question? Question number 3. In a centrifugal pump, what causes leakage losses? Is it option A, fluid escaping through clearance between the impeller and casing? Is it B, energy loss due to reverse flow circulation? Is it option C, vortex breakdown near the inlet? Or is it option D, reduction in shaft speed? What do you think? Okay. Okay, sorry, there was a bit of a technical issue on my end. So we are back now. Coming back to question number 3 of today's session, it's asking us that in a centrifugal pump, leakage losses are primarily caused by what? Is it option A, fluid escaping through the clearance between the impeller and the casing? Is it option B, the energy loss due to reverse flow circulation? Is it option C, due to vortex breakdown near the inlet? Or is it option D, due to reduction in the speed of the shaft? Let's take a look at the solution. It's actually option A. It's due to the fluid escaping through the clearance between the impeller and the casing. So basically, any rotating part, for example, let's say the blade of a turbine, that cannot be completely in contact with its casing, right? So there has to be a small clearance between the two. So what happens is that some of the fluid, it actually, instead of going through the vein, it leaks out through these clearances because there's a pressure difference between the two ends. The outer end, the outer radius in case of a pump or a centrifugal pump in particular, the pressure is higher, whereas in the near the hub or of the blade, the pressures are lower. That's the suction side of it. So as a result, through these clearances, the fluid flows in the opposite direction than what we intended to travel in. So due to that, the effective flow rate is reduced. There is some leakage, as the name suggests, and that's what leakage losses are. Leakage losses are caused by that. Okay, so moving on, we'll move on to question number 4 now, which is asking us that in a velocity triangle for a radial flow pump at the impeller outlet, the blade angle B2 is defined relative to what? Is it option A, the meridional direction? Is it option B, the tangential direction? Is it option C, the direction of absolute velocity? Or is it option D, the direction of relative velocity? So I'll draw a picture for clarity. So I'm just showing one blade connected to a hub and it's rotating. So at the outlet of this radial flow pump, how is the blade angle beta 2 defined relative to? Is it relative to the meridional direction? Is it relative to the tangential direction? Is it relative to the direction of the absolute velocity? Or is it related to the direction of the relative velocity? All right, so let's take a look at the solution. It's actually option D, related to the direction of the relative velocity. So, at the end of this blade, so the fluid comes out tangentially, and that's W1 or 2 rather, then the blade is moving in a certain direction, so that velocity is u, and uh, the relative velocity is the one in between. So not the relative, the absolute velocity. So now the blade angle beta 2 is defined as the angle between the uh, tangential direction, the direction of the relative velocity W2 to the direction in which the blade is moving, that is U. Okay, move on. We'll move on to question number 5 now, which is asking us that reverse flow circulation at the pump inlet results in what? Option A, decreased mechanical efficiency. Option B, increased cavitation risk. Option C, negative slip factor. Or is it option D, reduced volume flow rate? So let's say if we have an axial flow pump like this. This is the blade, this is the center line, and it rotates in a certain direction. And the fluid is coming in from left to right. And if there is some reverse flow circulation over here at the pump inlet, what does that result in? Is it option A, decreased mechanical efficiency? Is it option B, increased risk of cavitation in the pump? Is it option C, negative slip factor? Or is it option D, reduced volume flow rate? Okay, let's take a look at the solution. It's actually option D, reduced volume flow rate. So if we go back and see, so if there is recirculation, what does that mean? That basically means that the direction of flow is reversed. So whatever flow is supposed to come in, a bit of that goes back in the opposite direction. As a result, the total flow rate uh, gets reduced effectively. And that leads to all kinds of detriments to the performance of the pump or the turbine, whatever. So reduced volume flow rate caused by flow recirculation, that is something we do not want. Okay. Right, and another important part about this is that flow reversal really happens only when the turbo machine is operating at very much of an off design condition, like at design condition or anywhere near it. Such kinds of flow recirculation uh, has very little chance of happening, almost no chance. So it's only when it's operating at a very different set of conditions, maybe a very different speed or very different flow rate. In those cases, there is a chance of flow recirculation. Okay, so let's move on. We'll move on to question number 6 now, which is asking us that when frictional losses and bearings dominate in a pump, which efficiency is most affected by it? Is it option A, the hydraulic efficiency? Is it option B, the volumetric efficiency? Is it option C, the mechanical efficiency? or is it option D, the overall efficiency? So there are, shafts in almost all forms of turbo machines, and those shafts have to be held by some form of bearings, either ball bearings or journal bearings. And if the frictional, and of course there are some unavoidable frictional losses in any form of bearing. So when those frictional losses in the bearings in a pump become higher, which of these four efficiencies do you think will get affected the most, percentage wise or whatever? Is it option A, the hydraulic efficiency? Is it option B, the volumetric efficiency? Is it option C, the mechanical efficiency? Or is it option D, the overall efficiency? Okay, let's take a look at the solution. It's actually option C, the mechanical efficiency. So, you know, the mechanical efficiency is the efficiency uh, which takes into account all the mechanical losses in the turbine. And one big part of it is this bearing friction losses of the main shaft of the turbo machine. And so if frictional losses in the bearings, if they go up, then it's the mechanical efficiency which will be affected the most. Now, of course, as a result of that, the overall efficiency will also suffer. But in particular, it's the mechanical efficiency which is tied to the frictional losses in the bearings, as well as other mechanical losses, which are not related to the flow or the impeller in any way. Okay. All right. So let's move on. We'll move on to question number 7 now, which is asking us that the meridional velocity in a turbo machine refers to what? Is it option A, the tangential component of absolute velocity? Is it option B, the velocity component in the direction of fluid flow through the machine? It could be along axis or radius, depending on whether, or a combination of the two, depending on whether it's an axial flow device or a radial flow device or a mixed flow device. And option C says that it's the velocity of the rotor, and option D, it says that the velocity normal to the flow. So the meridional velocity in a turbo machine. What does it mean? What does it refer to? Which velocity uh, does it represent? Is it option A, the tangential component of the absolute velocity? Option B, the velocity component in the direction of fluid flow through the machine along axis or radius? Option C, the velocity of the rotor or the runner or the blades, whatever. And option D, the velocity normal to the flow, that is, whichever direction the flow is going in, whether that velocity itself is called meridional velocity or not. Sorry. Okay, so what does the meridional velocity in a turbo machine refer to? Is it option A, the tangential component of absolute velocity? Is it option B, the velocity component in the direction of fluid flow through the machine? It could be along the axis or the radius or both, or a combination of both, depending on whether it's an axial flow or a radial flow machine or a mixed flow machine. Then is it option C, the velocity of the rotor, runner, impeller, blade, whatever you call it? Or is it option D, the velocity normal to the direction of the flow? Let's take a look at the solution. It's actually option B. It's the velocity component in the direction of fluid flow through the machine. I mean, it's the velocity of flow minus the rotational component. So basically, this will be most clear if we take, the uh, if we take the example of a mixed flow machine where this is the axial direction, this is uh, the center line through which it rotates. So there is a radial component as well as an axial component, right? So if I'm sorry, so if I'm focusing on this velocity here, then it has an axial component as well as a radial component. So if I call them CR and CA, radial and axial, then the meridional velocity CM would be the resultant one. So square root of the sum of squares of the two, the axial component as well as the radial component. Now, which part of the absolute velocity of the fluid does it ignore? It ignores the rotational component. So there's a, you know, if it rotates in this direction, then there is a velocity component in this direction as well, c phi, let's say, in the azimuthal direction. So that's not part of the meridional velocity. So the meridional velocity actually becomes really important when you're trying to uh, draw the velocity triangles and solve for it. Over there, the uh, CFE and the CM would show up in a different way. Okay. All right. So let's move on. We'll move on to question number 8. Now, you have to do a bit of math for this one, but very simple one. So, what does the question say? It tells us that there's a pump which delivers a certain volume flow rate of water, which is 0.12 meter cubes per second, and at a head of 20 meters. So, that's the pressure increase due to the work done by the pump. And we know that the overall efficiency of the pump is 80%. What we have to calculate is the required input power, or whatever electrical power that you are supplying to the motor which is driving the pump. Is it option A 23.7 kilowatts, option B 29.4 kilowatts, or is it option C 36.8 kilowatts, or is it option D 19.6 kilowatts? Sorry. So take your time, do the math. It's a little bit of it, but do it carefully. And once you have figured out the solution, sorry, you can either type in the chat box or you can unmute and answer as well. Also, another piece of information which you might need is that the density of water is 1000 kg per meter cube. G, take it as 9.81 meter per second square. So given this set of data, how do you find the required input power? So the volume flow rate of water is given, the pressure increase, the pressure difference created due to the pump is also given, the head gain actually, and also we know the overall efficiency of the pump. We just need to find the required input power. So let's take a look at the solution. It's actually option B, 29.4 kilowatts. So let's get there. So basically, you know, the input power is higher than the power supplied by the pump or the compressor to the fluid. So PC over P in, which is the required input power, that is the overall efficiency, which is 80% in this case. And the second piece, the power supplied by the pump to the fluid, that is equal to uh, rho GH into Q. So if you just plug all these things in, so then P in becomes PC by eta naught or eta O. PC we know as rho GHQ divided by eta O. Now just put the numbers in. So we know the density of water, we know G, 20 is the H given, and the flow rate is 0.12, and everything is in SI units, so you don't have to worry about converting things, and divided by the overall efficiency, which is zero point 0.8. So let me just quickly calculate this to confirm. I have 981 into 20 in a 0.12 divided by zero point 0.8. So that gives me 2943 watts actually. 2943 watts. That should give me, did I do it correct? 0.12 into 20. Oh yeah, sorry, there's another zero. So 29,430 watts. So that's basically 29.4 kilowatts, which is the answer. And that matches with option B. Okay. All right. So let's move on. We'll move on to question number 9, which is asking that in a turbine, the degree of reaction is defined as what? Is it option A, the ratio of the actual head developed to the total supplied head? Is it option B, the ratio of static pressure drop in rotor to the total energy transfer? Is it option C, the ratio of kinetic energy at exit to that at the entry? Or is it option D, the ratio of the world component velocity to blade velocity? What is the degree of reaction? You know, in any turbo machine for that matter. In this case, the question has the word turbine in it, but really it doesn't matter. So is it the ratio of the actual head developed to the total supplied head? Is it option B, the ratio of static pressure drop in the rotor to the total energy transfer? Is it option C, the ratio of kinetic energy at the exit to that at the entry of the turbine? Or is it option D, the ratio of the world component of velocity to the blade velocity? So basically, the degree of reaction is really the change in pressure across, it's related to the change in pressure across the turbo machinery. So there are basically two kinds of devices uh, depending on their principle of operation. One set of or one class of turbo machines are these impulse machines, uh, in which there is no change in pressure of the fluid flowing through it. Whereas reaction devices are or reaction turbo machines are those where there's a very uh, specific or significant change in the pressure of the fluid across the turbo machine, and especially in a turbine in this case. So the degree of reaction is the ratio between what part of that work done, uh, or sorry, what part of the energy transfer from the fluid to the blade happened through its change in pressure to uh, the total change in the enthalpy of the system. So basically, you have to look at the total static pressure drop to the total energy transfer. So in terms of uh, enthalpy, it's written as the difference between the static portion of the enthalpy to the stagnation enthalpies. Right. So the difference between the stagnation enthalpies, that's the total energy transfer, and the static pressure drop, that's captured in the difference in the static enthalpies from one end to the other of the turbine. Okay, hope that's clear. Let's move on to the last question of today's session. Question number 10. So it's asking us that it's telling us that water enters a radial impeller of a pump at a velocity of 12 meters per second at an angle of 20 degree to the tangent. The blade speed at the inlet is 18 meters per second. What you have to find is the relative velocity at the inlet. So you have to draw a velocity triangle and find out what the sorry, you have to find out what the relative velocity is. Okay, so let's see how to solve this. The answer is 7.9, but how do we get there? So first write down what are the things that we know. We know that the absolute velocity is 12 meters per second. So C1 is 12 meters per second. Then the blade angle beta 1 is 20 degrees. Or sorry, no, that's the not the blade angle, that's the meridional angle, that's 20 degrees to the tangent. That's the angle made by the absolute velocity with the tangential velocity. And the blade speed at the inlet is 18 meters per second. So U1 is 18 meters per second. So if we try to draw the velocity triangle, it would look somewhat like this. So the this is the absolute velocity c, this is the blade's velocity u, and this would make it the relative velocity, which is what we want. These are all 1. And this angle, alpha 1, is 20 degrees. So we know these two numbers. This is the number that we have to find. So basically, you can drop a perpendicular here. So what would that give us? So, you know, this part of it would be u1 minus c1 cos alpha, and this height over here is c1 sine alpha, and this is a right angle triangle. So from that we can write that w1 being the hypotenuse is the sum of the squares of the two. So c1 squared sine squared alpha plus u1 minus c1 cos alpha whole squared. And let's put in the numbers here. So let's find out what C1 sine alpha is. So the sine alpha 1. I'm forgetting the 1 everywhere. Sine alpha 1, cos alpha 1, cos alpha 1, sine alpha 1. Here also C1 sine alpha 1. So let's do the math. So sine of 20 degrees is 0.34. Multiplied by C1, which is 12. So 4.1 meters per second. And let's find the other component, U1, we know, minus C1 cos alpha 1. So U1 is 18 minus 12 multiplied by cos alpha 1 times 20. So that's like 6.7 something. Now, if we take their squares and sum them up, let's see what we get. So 4.1 squared plus 6.7 squared gives me 61.7. If I take a square root of that, I get 7.85 something, which can be approximated as 7.9 meters per second, which is the answer, which is option A. So hope that's clear. That's all for this week. We will meet again next week at 3 o'clock. Thank you.